And so then I leave you the floor, Moataz, to start your presentation on strategies for functional grading. Thanks a lot.
Thank you very much for the invitation, and thank you all for joining us today to listen to the talk on functional grading. So the talk is somehow a number of studies. I'm not focusing on a single case study, although one of them will take a greater share than the others. But essentially, I wanted to put together all the work we have been doing on how to use additive manufacturing to create a microstructure that may be functionalized according to the required performance. So the outline of the talk, I'll talk about the concept of functional grading initially, and then I'll talk about the 3 examples of case studies of functional grading. The first one is on microstructural grading, where you change the microstructure by additive manufacturing parameters. And then I'll talk about chemical grading, where you change the chemistry across the build, and accordingly you change the alloy chemistry. And then I will talk then finally about lattice grading, which is also in a way to change the micromechanical performance or the mechanical performance of lattices, which obviously lattices have been quite fashionable these days with people who do additive manufacturing. Basically, the idea of functional grading has been around for some time, and the idea that you can have a property variation across an interface fascinates many people. So you can see here, this is an example of basically a weld on top of a forged Inconel plate. You can see here you have the forged microstructure at the bottom, and then you have the weld on top of it. But in a sense, you have the property variation across these 2 ends. So the nice equiaxed twin containing microstructure is very good for tensile strength and low cycle fatigue strength. But then the coarse-grained microstructure is ideal and good for creep and fatigue crack growth resistance if you need that. And if you have a structure that is facing 2 different performance requirements in the same component, that will be ideal. So one of the case studies which is available in the industry is the so-called dual microstructure disc, which basically has 2 different microstructures. One of them is close to the bore, where you see more fatigue loads, higher tensile stresses, and so it needs to be fine grains, more strength in there. But then towards the edge, where you have all the blades in, this is where higher temperature is seen. You basically have a coarser grains, larger grain structure, which is in this case can help you with creep resistance and fatigue crack growth resistance. So now this is achieved via complex heat treatments, via complex forging schedules to ensure that we have different microstructures at different locations. Now, additive manufacturing does give us that potential. So over the years, many papers came out on people using additive manufacturing to tailor the microstructures, or at least even play with the microstructure. One of the first one was an attempt on orientation, the work done by Suresh Babu and colleagues, looking into RCAM using electron beam melting to basically create a microstructure which is different by changing the heat and line heat sources in the process. And then some of the work we did in Birmingham around 6-7 years ago, where we used direct laser deposition, or DLD, to generate nickel-based superalloys. Both are fully dense, both don't have any defects as in cracks or pores, but they have completely different microstructures. One of them is more finer, one of them is much coarser and larger grain. And that's by tailoring the heat input. Beyond that, other groups looked into changing the laser power in the middle of a build, done in this case by SLM, to look into changing the grain from a fine grain into a coarse grain back into a fine grain. So somehow, if this can be utilized, if the potential of this can be used, we might end up having the ability to tailor the microstructure and achieve what people consider as the holy grail of additive manufacturing, where we can tailor the microstructure locally and generate properties on demand if we want to do that. So the first case study I'll talk about briefly, as much as I can, is the case of using dual microstructure components via laser powder bed. Now, this work was published in Additive Manufacturing, where we looked into creating a blade that has 2 different microstructures at the root and on the blade end, where in this case we looked into mainly changing the scanning strategy and other process parameters. And as you can see, it has other impact on texture and so on. So this program looked into how we can manipulate and grade the microstructure in Inconel 718 by powder bed fusion. So initially, we looked into the processing window for this alloy, and Inconel 718, like many other engineering materials that we process by additive manufacturing, they do have a very large operating window. They do have a large window where you can get good parameters. So you look into all these samples that you see in front of you, all of them are dense, all of them don't have much porosity. You're talking about 99.9 and more % of density and nominal density. And they are fine, no cracks, don't see much, keyholing or anything like that. Once you establish that processing window, then you can look into how those different samples have affected the microstructure, mainly the grain structure and the texture, as well as playing with the scan strategies, which I'll talk about in more details in a minute. Finally, look into the impact of that on the microstructure, grain structure, and texture. And from there, we move into trying to do and create graded structures, where we build a shape that has half of it is made of one microstructure, the other half is made of another microstructure, and then use techniques like digital image correlation to try to see how it behaves in a mechanical point of view. And then I'll give a glimpse of the work we did, where we tried to use that grading or that control of microstructure for oxidation related improvements or tailoring of properties. So I guess many people today talked about laser powder bed, and you know how it operates. I mean, we use in Birmingham the M2 system, which has typically what's known as the island scan strategy. You divide the build into patches, and these patches have an island size, and then the islands would shift from one layer to the other. Nominally, in the standard parameters, it will move 1 mil in the X, 1 mil in the Y, and that can help you somehow randomize the microstructure as you build along the layers. But what we did was that we said, well, why do we have to stick with kind of these scanning strategies? Why don't we try different scanning strategies? Now, our machine can do more. We can do the island, the so-called island parallel, where, as you can see, the scanning between the two layers, the laser vector doesn't turn 90 degrees between the two layers. And then we have the so-called unidirectional strategy, where between the two layers, you're going back and forth, back and forth. And then you have the cross-hatching strategy that can be also amended. Again, some of the flexibilities that I presume not so many people look into them is that control between, or the control of the island size. So you can change the shape or the size of the island. It doesn't have to be 5 by 5. You can have 2 by 2, 1 by 1. It's up to you, really. The impact, of course, is going to be on the process speed, but in a sense, you can control it. And then that island shifts, where how much each patch will move between the subsequent layer in X and Y. You can also change that. Over and above that, we also looked into the rule of thumb that everybody hates, but everybody uses, the energy density, where you can change the laser parameters and laser power scan, speed scan, spacing to generate different heat inputs. All of them, this is just a semi-empirical number to calculate, an equivalent heat input. As I said, everybody hates it, but everybody uses it, or many people use it. But it does give an indication of how different parameters may affect the microstructure. So now we got all of these conditions that I showed you before. Many conditions with different scanning strategies, different laser parameters, all of them are good. Now, how do we sort them, and how do we sort them quickly? The quickest way we tried to sort them was using X-ray diffraction. So if you do XRD for a powder, you get, for a nickel superalloy powder, you get a strong 1-on-1 peak. And what we did was that we tried, as you build a solid material, then you start to get a strong OO2 peak. Obviously, this is the favorable, solidification directions and so on. So you end up having very strong OO2 texture. We calculated the ratio between these two peaks and I'll show you how this was quite useful in OI. So that's one condition. That's the nominal. That's if you buy the machine, probably you will optimize and use these parameters. But what we have done, we looked into different angles of shift. So we can shift the islands big distances. We've looked also into smaller islands. So this is the 3mm island. And I want you to see how big we're getting in terms of the peak height between the two. This is a way to, what we used it is that we use it as a way to assess the directionality in solidification. Luckily, the spot size of X-ray is big. You can scan large areas quickly. Each sample can take, a few minutes, and you end up getting a good XRD pattern. From there, and by calculating those numbers, we then calculated the texture coefficient, which is used widely, in fact, in many studies. So I was talking to Giovanni from BAM, where he showed me a very nice paper about the use of the texture coefficient to assess the development of textures. Now, when we plot the different conditions with the energy density, we can see that there is a slight increase in that texture coefficient. So the directionality seems to increase. But of course, as you know, the energy density is not a perfect condition. So between these 2 points, we only increase the laser power. So you can see that when you increase the laser power, there is some increase in the texture coefficient. When you decrease the hatch spacing, again, you get increase in that texture coefficient. And then when you decrease the scanning speed, you get a jump in the texture coefficient. Because these are all non-standardized parameters, so they in a sense that it can be a little bit difficult to generalize this, or to say that these effects of texture are consistent in all ranges. So just take these with a pinch of salt from me. Now, if you look into the influence of the other parameters, the scanning parameters, so you can see that from the powder all the way to a different X and Y shift for the islands, we were able to get the texture coefficient to change significantly. Here for the powder, it's a stronger 1:1:1, obviously, whereas in that case we are getting here an 8 as a ratio between the two. My student only arranged them in an ascending order, so the change here is island shift 4, shift 2.5, island size 7, and until the end. And the nominal condition that people would normally use is that previous one. So the island perpendicular, that one here, is the one that people would use if they use the machine and optimize it and stop when they get the first dense condition. We continued to see that here we get very strong columnar grains. At the bottom here we get very more uniaxial microstructure, or more equiaxed microstructure. But we took it now to EBSD now to try to visualize it easier. So moving into EBSD, and I'm looking here into one parameter, which is island size. So changing from a 3 mil island, where the laser just moves in 3 mil distances, to 7 mil, where the laser moves into much longer hatches before it changes direction, you can see the difference in the grain size. We used SEM and to characterize the solidification cell size, and we can see that somehow between 3 mil and 7 mil, if our estimate is correct with all the errors and things like that, cooling rate seems to have doubled by moving into a larger island strategy, or a larger island scanning, larger island size. So this is the island size, again, to remind everyone, and that's the shift between the islands, which I'm yet to show you. So we just use the equations from the literature for solidification of Inconel 718 to find out, and just empirical equations, to try to find the typical cooling rates that are experienced. But you can see the difference. Big, strong texture columnar grains, more randomized, more equiaxed grains. They are not perfectly equiaxed, I have to admit, but in a sense more randomized in the texture and less columnarity to some extent. Now we try to see if we can predict that. So we had to call on the help from our friends at ESI Group to help us to see how we can predict the microstructures, which was not easy. The key problem in trying to predict the grain size and during solidification is basically to estimate the nuclei density. That Ng number is the nucleation density. And you can see here we tried different time steps. So from here to there to there, here to there to there, with different starting nucleation density. That didn't take us anywhere. So what we had to do is that we had basically to calibrate that by experiment. So we tried different parameters and we tried different nucleation density to see if we can predict that, predict the grain structure, and predict basically the level of columnarity or the level of equiaxed microstructure. To be fair, that's still work in progress. In a way, we were able to fit the model, but fitting the grain predictions with the results, I think it's going to take some time until that models become more robust. So I'll jump into the other effects. So we looked into island shifts. So how much shift do we move between islands? Is it a 4 mil? So basically the islands move a little bit far from each other with the next layer, or a 1 mil shift, where you have, as you can see, much stronger texture and large coarser grains as well in that case. So, and that's potentially easy to explain. I mean, when you have a 1 millimeter shift, you basically move just tiny bit from one to the other. So you keep the thermal footprint moving between the layers. Whereas if you do a 4 millimeter shift, you jump out of sight completely from, when you move in the order of your layers, you just move a little bit far away. So the thermal heat input is no longer easier to build up. as you keep moving from one layer to the other. So now we control the microstructure. What if you want to keep the grain structure? And that was a key question that we were asked. Can you keep the grain structure? And we found some heat treatments where we can get rid of the Logés, the niobium-rich segregation byproducts, get some delta. You don't win all the time, but you can retain the grain size while you are after the heat treatment, but you can regain back some of your strength that you achieved in the material. And that was one of the key things we wanted to look at. Once this was verified, we moved into the case study that I showed at the beginning, which is how to build a structure with two different microstructures from the bottom to the top. So the blade served as a case study to show that, yes, you can, if you change the parameters, you can end up tailor the microstructure from one end, tailor the texture if you can, from one end to the other. I would say there's still more work that needs to be done to control the thermal footprint of the laser and the influence of the scanning strategies. But in a way, it's a step in that direction anyway. Now, what about testing? So testing, we try to create different grading types. One type, which is a gradual grading, where we know the grain size, so we can change from fine grains to coarse grains over maybe 5 or 6 different parameters. Then we have the dual grading, so just two materials, high texture, low texture, and with a sharp interface between them. And then we looked also into what we call dual complex grading, where we have essentially one microstructure that is surrounded by, basically in a ball and socket joint. Try to imagine this in a microstructural context, that has a ball and socket joint of the two microstructures together. Now, the problems we found is now that once you build a cube or a blade, that's way different from if you build a big sample, tensile sample, or a component. The effects that were quite drastic in the case of a cube or a small sample are different from if you move into building a tensile sample. Despite this, they do still hold. We know that if you change the island size, island shift, yes, you can get, so that's the same sample where we change the two parameters, and you can see that there is a difference between the two in the microstructure, and that did hold at the end. Now, we took that to the next step, which is digital image correlation, to look into the basically testing across the interface. And as you can see, this is the interface of the sample. Here is the fine grain, here's the coarse grain. Now you can see that the different parts of the material, they behaved in a different way. Now this is only the room temperature test, so we're still working on the high temperature tests, and I hope that at some point we'll be able to report you these results in the very near future. What else can be done, briefly, before we close this case study? One thing that people can also do by functional grading is tailoring the oxidation resistance. Was a good report that was published in 2014 by Dongdong Gu and his group in Nanjing, looking into how different conditions of a nickel superalloy built with different heat inputs can control the oxidation rate. And you can see there is a difference between them. And that is affected by the grain size, texture, inhomogeneity, and so on. So our preliminary results, again, yet incomplete, we can see that there are differences between the different conditions. But interestingly, we get different oxidation results based on which plane you're looking at. And this is where it can be complex. So if you're looking at the XY plane, and that's the top of the build, you get an oxidation behavior different from if you look into the XZ plane, which is the side view along the build direction. So it needs a lot of thinking now how to move this into the case of a component at the end. So in conclusions, the texture in grain size can be increased, decreased by using the scan strategy and laser parameters. You can see that the island scan strategy was probably the most effective way of controlling the texture and controlling the grain size. Heat treatment was defined so that we can retain the microstructure, retain the grain, retain the grain structure, grain specifically, not other features. And the graded microstructure were developed, and we tried to show how they might be used in the case of improving the mechanical or impacting the mechanical behavior and the oxidation behavior. So that's the first case study. We'll move now into the second one, which is functional grading during DLD. Okay. I think my presentation crashed.
Can you try
Yeah, just one more time.
Yeah.
Just need to share again your screen.
Yeah. Okay, so you see it again?
Yeah, but we are seeing your presenter view. Can you change?
Okay.
Swap displays? Yeah.
Okay. And yes, so you can see functional grading during DLD, right?
Yes.
Yes.
Fantastic. A few years back, we developed in Birmingham a multi-wire direct laser deposition system. And people use powders all the time, and powders with DLD can be a little bit tricky because you have to blend powders and spray from different hoppers, and there's sometimes contamination issue. The powders, sometimes they do not all fly into the melt pool with the same amount. So what we've done is we made a system that we can feed up to 6 different wires into it. They can be elemental and they can be alloyed. And each wire is controlled by its own speed, basically. The wire feeder has its own speed. And the way it works is that all the wires will meet at the focal point of a laser, and then they will melt, and then we keep dropping them one after the other, and we build the shape in this way. Now, the good thing about it is that it's a very good technique to try to rapidly build the new alloys and also look into creating bimetallic or functionally graded structures. And this also can be potentially used in context with DLD to do this. Let me show you how it works. So if you can see the video, so you have here 3 wires in this case, 3 wires coming together at different speeds. Now they join up together, they start to melt and homogenize while the laser is heating them. And as the weight of that ball becomes too heavy, it drops. You can see that the laser still heats the bottom part. You can see still red hot at the bottom. So it does get a little bit of homogeneity at the end. Now, this is the good thing about it, is that it can give you, if you have elements of a similar melting point, you can do good accuracy of compositional accuracy up to 1%. Obviously, if you have a material which contains, let's say, niobium and aluminium, that can be very tricky to build from elemental wires. But we have looked into a number of alloy classes to see how we can create functional graded structures by this approach. We looked into shape memory alloys, which is the case study I'm going to talk about in the next slide. Corrosion-resistant steels and gamma intermetallics and superconductors. On the shape memory front, so the way that we've been looking into this is that how we can grade the chemistry from the bottom to the top. So we did 2 different builds. The sample looks like the one you see here in the picture. The discoloration, obviously, on the surface comes from the residual oxygen in the chamber. But you can see that we have done on the right-hand side titanium nickel copper, on the left-hand side titanium nickel hafnium, and you can see that the hafnium content was quite linearly increased from the bottom to the top. The titanium content was decreased. We kept the nickel content constant while we're changing the 2 elements. And the same thing happened for we kept titanium content constant, or mostly constant, while changing the copper content in the other one. This approach is still under investigation. So chemical grading is another useful way, whether you do it by additive manufacturing, you do it by DLD in a wire form or a powder form, is another strong way to control and grade the microstructure from the bottom to the top. That's not all on DLD. And just to keep in the tone with the case studies that I'm talking about. So other work we've done, we looked also into another tool to grade the microstructure, which is using pulsing in DLD. Our TRUMPF DLD system in Birmingham has the ability to pulse the laser. And so we can do a continuous wave laser where the laser power is constant, or we can do a pulsing level where the power will drop down to 2% of the maximum, and then it goes up and then goes down, up and down, up and down. And using this kind of behavior, this kind of strategy, what we were able to do is that we were able to control the grain structure in a similar way. So these images are taken from titanium 6-4, where you can see that if you do continuous wave, you end up generating large grains all the way. You do get the fine grains at the bottom, of course, which because of rapid cooling. But then if you do pulsing, you end up creating more equiaxed grains throughout from the top to the bottom. And this strategy has a lot of impact and a lot of potential benefits, not just for functional grading, but other things, as I'll show you in a minute. But just to simulate how they look like, this is infrared imaging for continuous wave versus pulse wave. So if you look into continuous wave, we have the heat going back, forth, back and forth, back and forth. And then if you look into pulsing, you can see the pulsing effect. The heat does dissipate for a second and then comes back. But actually, the thing is that whatever happens in the material is essentially a competition between the cooling and the time you need. So basically, there's a critical time, or in other words, there is a critical frequency that you need to be pulsing at in order for you to be able to break up the microstructure. And that's what we tried to do in this study, where we basically looked into different laser frequencies. We went as low as 10 hertz and as high as 1 kilohertz with continuous wave as the comparison. Now, you can see if you look at the end of the build, the temperature difference. So this is the wall at the end of the build. At the end of the build, you can see obviously that as you go lower in the frequency, you end up generating a much lower heat, and potentially this may have some other benefits like residual stresses or so. And indeed, if you look into the temperatures, it did have a good impact on the maximum temperature recorded on the bottom substrate at the end. As you go down in frequency, you end up generating a colder weld. But you have to be careful. Don't go too cold, because that might give you, in this case, lack of fusion defects, for instance. So the benefit is also in nickel superalloy. So this is Inconel 718. And just to give you the comparison, this is now continuous wave, and this is pulsed wave. The same thing happens. You can control the grain structure. You can control the columnarity, the grain size, by changing from continuous wave to pulsed wave. But that's not the only tool available to us. The same thing also happens, as I mentioned in the case of SLM, with the laser power. So what you see in front of you here is, again, Inconel 718, one of the nice materials that people know how to process. And when you change the laser power from, very low, from 150 all the way to 1900, here is what you see. First of all, you don't see much defects. The material is still mostly dense. There are some tiny pores here and there, but they are tiny. They are not too many. I mean, they would obviously appear with, in this case, with high laser power, like 1900, because it's a keyhole defect. But you can generate a different microstructure from the bottom to the by choosing the right laser power while maintaining the other parameters constant. And that can be very helpful for you if you want to generate a functionally graded material. And basically, this is what we did. So we applied those different laser powers on a substrate, changing it from the bottom to the top. And you can see how the microstructure, after the initial part close to the substrate, you can start from a fine grains, coarse and coarser. And more importantly, you can also change the level of niobium segregation and the lattice phase that form as you move from the bottom to the top. So that can be another tool to control and grade the material if you play with pulsing, heat input, as well as talking about the chemical segregation or chemical modification. Now going to the pre-last case study, which is the case of functionally graded lattices, talking about how we can use additive manufacturing to build lattices that are functionally graded. Now, people know in nickel titanium, you have the standard, transformation from martensite to austenite and stuff like that, and how you can detwin the martensite, and if you apply load into it. Martensite has some interesting properties as a phase in nickel titanium. In most applications, stents, for instance, mostly they rely on austenitic nickel titanium, so it's an austenite phase. Whereas the nickel titanium has some interesting, abilities. It has this double yielding effect in it, but more importantly as well, it has a very low elastic modulus. So martensitic niti has a modulus between 21 and 69 gigapascal. And as you know, many people who try to do medical implants, they all the time try to look for a material with low level of with very low elastic modulus. So what we did, what we liked about nickel titanium is that, first of all, it has that asymmetric tension compression effect. This is nitinol, the compression and tension, and as you can see, it does behave like human bones to some extent. And it's very good about it is that it can do damping effect when compressive stresses are being applied to it. So the case study we had was, why don't we try to create a lattice that somehow simulates the bone? So human bones, they are usually dense from the outside and dense on the outside and loose in their density from the inside, if you look into human bones. And the way that we did it was that we, instead of building uniform lattices based on these unit sizes, we basically created a functionally graded lattice, which has its porosity changing from the outside to the inside. So at the edge, it has 40% porosity. So this is the unit cell, that the unit structure that you're using. And then on the inside, you can go into that tiny little one. So you can grade the microstructure from the outside to the inside. When we did that kind of grading, the most interesting effect we saw was what happens when you apply a mechanical load into it. And this is where we relied on digital image correlation to see what happens. So if you have a uniform lattice, you typically have that 45-degree band, and then you get some densification in the middle, and then things break, as usually 45-degree at the end in a uniform lattice. But if you generate a graded lattice, somehow the densification seems to move from the outside to the inside. And that's one attractive thing about how they behave. They behave like a sponge, basically, dense from outside, less density in the inside. So they behave in such an interesting way. We were able to create also very low density structures using this kind of strategy. So by basically, not low density, low modulus structure. So by tailoring the level of porosity inside the material, we can get into very low modulus, which is even way less than the human bones, in fact, getting to a level of around 5 gigapascal. Now, different deformation behavior, different low elastic modulus are all very interesting things that can potentially be of potential benefit if you want to create a lattice that is graded for shock absorption or for other applications. In 2 minutes, I'll give 2 additional case studies, and then I'll be done. So other ideas. One of the other ideas we had was relying on in situ alloying. So we did a project on titanium 12% moly. This is an alloy that we use, well, a model alloy for medical applications. And we rely on in situ alloying because sometimes it can be difficult to buy this alloy. And what we found was that we can use the heat input to the level that we can blend aluminum, titanium and moly and homogenize the chemistry to a large level. So we can dissolve most of the molybdenum as we keep increasing the heat input, as long as we make sure that we don't create keyhole porosity by getting the right process parameters. And the interesting thing is that with very high heat input, you end up generating single phase material, or just beta titanium with some alpha double prime or omega that is present in the material. So you can dissolve a lot of that. So this idea has to be attributed to my PhD student, who said, why don't we try to create a material that is a composite material that has half of it has some bits of moly still inside, and then some other bits which don't have actually moly inside. So essentially use in situ alloying to create a quasi-composite, well, it's a metal matrix in a way. So it has a sandwich-like structure. And this is what he did. So basically, there was in some layers, he would fire the laser at a maximum power or the required heat input to dissolve everything. And then in other layers, he would not dissolve the moly. And then again, dissolve most of the moly and then leave a little bit of moly. And basically creating that kind of sandwich structure of on and off to see if that's going to give us any improvement in the mechanical behavior or not. I mean, now, obviously, I tried to tell him to take it easy because obviously those undissolved moly will have an impact on mechanical properties, but at least on the tensile. But we wanted to look initially onto the compressive. And the good, interesting result we had was that, first of all, if you compare the low energy condition where you have a lot of undissolved moly with the high energy condition that had all the moly dissolved, and then you compare that with the composite titanium moly alloy, it seems to be generating a little bit of higher stress. So here is the engineering stress. Here is the true stress strain, a little bit higher. This is the work hardening rate between the different systems. So somehow we can generate a stronger material or a stronger sandwich type microstructure. In effect, if you can control the heat input to control the size of those undissolved particles, you might be able to get a nice, structure property contribution from this. Okay, now I come to the last slides. So basically tailoring behavior and properties can be used. I spoke with you about some tools where you optimize the parameters, optimize the laser source, optimize the system itself, which works on the chemistry, optimize or use multiple materials or lattices. Now, despite everything, despite all the work I've been doing, we're still looking for interesting applications. So that is, I think, is the part where the industry can potentially come up with some ideas about what we can do in the near future with these ideas. And by this, I thank you all for your attention, and I'll be very happy to take any questions. Thank you.
Thank you very much, Moataz, for the very nice overview of many different topics. So I see there is already one question from Manas.
Thank you, Moataz. It was a very nice talk. I have a question on the nickel titanium part of. So you mentioned that you change the composition of nickel and titanium, and you build the structure that is functionally graded. How much variation do you see in the composition locally with respect to what you wanted to have? Or in other words, if you wanted to create the same structure with the same composition, would you be able to maintain that composition throughout?
Now, this is nickel titanium, right? We're talking about nickel titanium. You mean the direct energy deposition, where we grade the chemistry from the bottom to the top?
Yes.
Yeah. So we have the ability to control. You mean? Can you say the question again one more time, Manas?
So if you put 50% nickel, 50% titanium, are you able to guarantee that at the end, once it has solidified and cooled down, you get 50-50 of both? Or
Right.
is there
Okay.
some loss?
No, it's not about losses. I would say that there is around 1% variation. Nickel and titanium, especially, luckily, they have close melting temperatures. Right. Now, we try to do titanium, niobium, aluminium a little bit when I had some motivation to work on gamma. I lost it completely now. But when I used to do some work on gamma, aluminium was a problem, because as you try to melt niobium, aluminium will evaporate.
Okay.
So if you are working with elements of closer melting temperatures, that works well. Whereas if you are working with elements of completely diverse melting temperatures, yeah, you're going to have problems, and that will need iterations and recalibration of your system.
And would you expect that the microstructure you get is homogeneous if you kept the composition constant?
No, well, the microstructure, it's a solidified microstructure. So heat treatments heat treatments are due. Okay, so as you know, titanium nickel system, for instance, it's known for its so many intermetallic systems that it can produce. So you will need a nice homogenization treatment to homogenize the chemistry throughout. Yeah.
Okay. And
not
do you
as
think
good, not good as fabricated, in full honesty. Yeah.
And if you have this 1% variation, does that affect the superelasticity or shape memory effect? Or
absolutely. Now you know, titanium nickel or nickel titanium are very crazy for their behavior. So just a tiny change in the chemistry can change your phase transformation temperatures, and that's mainly on the nickel. So basically, if you are, once the titanium starts to exceed the nickel, things start to change, rapidly. So yeah, you have to make sure that you are spot on when it comes to the chemistry. But that is not the case. So if titanium nickel system has its own concerns, but you can try the titanium nickel hafnium, titanium nickel copper systems, where you can get a gradient of phase transformations if you wish to do so.
Okay. So that's the solution you would propose to avoid these little variations that could change the properties. Okay.
If there is a system that is known for for being very sensitive to plus or minus 1%, then obviously you would avoid them, and you try to look into an alloy that is more suitable for such a process, for the process we developed.
Okay, very nice.
Thank you, man.
Thanks.
Any other questions? I don't see any for the moment. Maybe I'll ask one concerning the island strategy that you talked about at the beginning. I was just wondering, because there was a talk this morning by Steven van Petegem on really the influence of the scanning length vector, the length of the scanning. So the shorter it is, actually, the more you heat the material, So do you think that most of the effects that you describe relate actually to a local heating effect,
100%.
or is there something else?
You know, exactly. So as you walk in very small steps, the heat is not going to dissipate. So
Right.
you keep going back and forth. So you do a build-up of heat. Whereas if you move in, as you saw in our largest island, you know, 7 mil, back and forth, you are giving a chance for the temperatures to cool down. And as a result, the microstructure becomes more equiaxed, less columnar. So indeed, those critical time effects in the process can determine the microstructural and the solidification dynamics you're going to get.
And then you mentioned that the cooling rate was slower for the smaller vector lengths, I guess, because you have internal heating, and so the cooling, the difference of temperature is lower.
It's lower.
That's why you have a lower cooling rate.
Precisely.
Okay, thank you.
Thank you.
Or another question from Maria Teresa. You need to unmute yourself.
Oh, it's my fault again. Maria, you can try now. Sorry. Yeah, no, you can.
Sorry. Yeah, thank you. Really, thank you for the talk. It was really interesting. I have a really short question. You show in one of the slides that you are doing mixtures of titanium with hafnium and titanium with I think it was a copper alloy.
True.
Did you find problems in between, or when you have beginning to introduce the second component of formation of intermetallics, which will weaken your structure? And if yes, how did you react to this situation? How, or did you not care about, or did you try to avoid the formation of the this intermetallic not interesting phases in your case, maybe?
Yeah.
And yeah,
the process, thank you for the question. So the process runs in a continuous way. I mean, let me put the video one more time so that you can see how it looks like. Now swap displays. Yeah. So here is the video of the process working. So you can see that
yes.
the wires are continuously fed. They don't stop, okay? So, and you can program it in advance that you say that every, you know, 5 seconds or every 10 seconds, you change the speed of the wire. So you do get a relatively, when you look into the chemical analysis, despite everything, we do get a nice linear variation of the element because of the way that the process itself runs smoothly. So you keep just changing, reducing one, and increasing the second. This is how it runs. Now, in this system, in these two systems specifically, we did not experience cracking. We did not experience any, well, cracking obviously induced by the intermetallics, as your question probably was asking. But in other systems, we saw that, yes. So in other systems, once you start to change the elements, you start straight away to get cracks forming. You start straight away to see, as the material cools down, cracks opening up when you have a more, you know, aggressive intermetallics. The cooling rate, according to our estimate in this process, is around 10,000 degrees per second. Okay. Which also, you know, tells you something about the intermetallics. You know, they are not going to be too big, so that they're not like solidification. So the cooling rate is a little bit fast. It's a DLD cooling rate, and from that point we did not observe in these two systems specifically defects developing in situ.
Okay.
But we saw it in other systems, I admit.
Okay. Thank you.
Thank you.
And then another question from Charles-André.
Yes, thank you, Roland. I appreciated also the first part of your presentation where you show that you also want to manage to have a gradient of microstructure in your internal 718, not just composition. And so you want to have columnar or equiax and various textures at various places of the part. And for that, indeed, modeling could be maybe useful. So you show a few simulations where you explain that optimization of the parameter like nucleation density is one of the important things to be done. But in this model, there might be other parameters like nucleation and undercooling or size distribution or undercooling distribution for the heterogeneous nucleation particles you may have, or it might also be another origin for the formation of new grains that is fragmentation, not nucleation at all. So I think for all these things, there might be more to be studied. And so I'm wondering, with respect to modeling, if you have started to work on these various other parameters.
I didn't get, I don't know if it's just me, but I didn't get the last bit of the question. So nucleation density.
Okay. Yeah, nucleation density, fragmentation might be a parameter.
Yes,
the growth undercooling of the dendritic might also be another parameter that you need to compute for multi-component oil. I mean, there are so many parameters in this model, so you just mentioned one.
Yes,
tell us more about global.
Exactly. Well, I have to admit, our solution is more iterative, less scientific. I mean, we basically, we estimated the nucleation density, right? And as you rightly said, the problem is way more complicated. So there are, as you say, fragmentation, there are nucleation, there are other effects happening. And even with our best modeling capability, we were not able to look into or actually keep the process progressing in the predictions more than 2 layers. Okay, so we just tried 1 layer or 2 layer, and even that takes a very long time in calculation. That's I think another thing. So trying to come up with a good model that reflects the true physics, I cannot say that we have done it, and I think it's going to be very difficult to try to get a model that reflects the true physics.